Let's look at the first example on topological sorting. So this is a problem from LeetCode. It's called the course schedule 2. So here's the problem description. So we have 10 n courses that you have to take, and the courses are labeled from 0 to n minus 1. And then, as you all know, courses have prerequisites. So for example, if course 1 is the prerequisite of course 0, meaning that in order to take 0 you have to first take 1, then this is expressed as a pair 0 1. So in terms of graph, this is really an edge from 1 to 0. It says that you have to take 1 first and then you can take 0. So the input for the problem is the total number of courses and then the list of the prerequisite pairs. And you're asked to return the ordering of courses that you should take in order to finish all courses. If there are multiple correct orders, you can return any one of them. If it's impossible to finish all the courses, this will happen when there's a cyclic dependency. For example, in order to take 1, you have to take 2, and in order to take 2, you have to take 3. In order to take 3, you have to take 1. Then there's no way to finish all of them. So in that case, you should return an empty array. So here is an example. We have 4 courses and also 4 dependency. So the first course says that you have to take 0 before you take 1, and similarly you have to take 0 before you take 2. So essentially you have to take 0 and then you can take either 1 or 2. And then the last 2 condition says that in order to take 3 you have to take 1, and in order to take 3 you have to take 2. So course 3 has 2 prerequisites, both 1 and 2. So given this requirement, there are essentially 2 ways to take these 4 courses. You have to take 0 first and you have to take 3 last, but the order between 1 and 2 either way will work. So there are 2 possible output. You can return any one of them, it will be considered correct. So this is a topological sorting problem. So topological sorting is a linear ordering of the nodes or vertices in a directed graph. It have the property that for any edge from U to V, then U must come before V in the ordering. So in this case, there's an edge between U and V. From U to V means that U is a prerequisite of V, so you have to take U first before you take V. So you can take other courses in between V and U, that is okay, but U has to come before V in the ordering. And the topological ordering is possible if and only if the graph has no cycles. So given a directed graph, and if it doesn't have a cycle, it's called a DAG, which stands for directed cyclic graph. So the topological sorting algorithm will also be able to determine whether the graph is a cyclic graph. There are 2 algorithms. There are 2 sort of common algorithms for computing topological sorting. One of them based on breadth-first search, which is called this Kant's algorithm. The other is based on depth-first search. So here we'll just talk about the Kant's algorithm, which is based on BFS. So the algorithm, I think it's fairly easy to understand. So essentially you start from all the nodes that have no incoming edges. So any of these nodes can go first because there's no other nodes pointing into it. So in terms of courses, these are the courses that have no prerequisites. So you can take any of them. So we put all of them into a queue. Here it's listed the set. For this problem, it's kind of equivalent because it doesn't really matter which order you take when, for example, 2 courses, none of them have any prerequisites. So in this algorithm, we put into a set. So while the set is not empty, we will take 1 from the set and then add this to the list of courses that we will take. So L is the output. L will eventually be the list of all courses you can take in the context of this problem, all courses you can take. So this node n or this represent the course, uh, we are saying we have taken this course. Now we can check all the other courses that require this course as a prerequisite. We can say this prerequisite has been satisfied. So that can be represented as removing the edge from the graph. And then if this other course has no other incoming edges, then that means all the prerequisite has been satisfied. So then this course is now ready to be taken. So we add that into the set S. So this loop will go on until the set S is empty. So when we exit the loop, we can check whether we have performed a full topological sorting, and there are a few different equivalent conditions for checking that. The pseudocode on this slide says if the graph still have edges that has not been removed, then that means there's still things in the graph that we have not added. So that means the graph has a cycle. If the graph has no edges at this point, then we can return L. So equivalently, we can check how many elements are in L. So if the graph has n nodes and L include all n nodes, then we're done. So we have performed topological sorting. On the other hand, if the L has less than n nodes, then that means there are still nodes who have not been added, and that can only happen because there's a cycle. So let's look at the code for this problem. So this is my Java code. So I declared two integer arrays. This answer will store the final topological sorting order, and this represent in degree. IND represent in degree. So I store the in degree of every node, and this is the value that will be updated in this algorithm. So whenever a node have an in degree of 0, then it's ready to be taken. The course is ready to be taken. So in this algorithm, we want to use adjacency list because for any course, we want to enumerate through all the courses that this course is a prerequisite. So in order to do that efficiently, we need the adjacency list. But the input is given in the form of edge list. So this prereq is a list of pairs. So a list of two element integer array. So it gives us a list of edges. So we need to sort of convert that representation into adjacency list. So we first create this adjacency list. As I mentioned in the previous video, we use an array list of array list to represent the adjacency list. So A is for adjacency list. So we create the object, and then we create all the empty array list for edges and add it into this A. So this 3 lines sort of initialize the adjacency list. At this point, this A represents a empty graph. And then for every edge that is in prerequisite, I will do two things. One is I will increment the in degree of the first element, because they give the two number is pointing from the second to the first, from E1 to E0. And the second thing is I add that edge into the adjacency list using this line. So after initializing the adjacency list, we can use Kahn's algorithm for topological sorting. So we start by creating a queue. Again, I use an array deck, and the queue is initialized to include all the nodes that have in degree 0. So that means these are the courses that have no prerequisite. So I loop through all the nodes and then check if they are in degree 0. I add it to the queue. And this I use that to indicate how many nodes have already been added to the answer. So this serves both the purpose of assigning each new element to the correct position in the array, and also for checking the whether I have added all n element. So if I use array list instead of array, I don't have to use this variable I. But I prefer array to array list whenever I can, because it's uses sort of less memory and slightly less efficient, slightly more efficient. Okay, so while the queue is not empty, I will take element out and then add it to the answer. So this answer array will store the topological sorting at the end. And then for each node that is directly reachable from X, for each Y, each course Y that has the X as a prerequisite, I will decrement the in degree of Y, and if after subtracting 1 from the in degree, if it's 0, then I'll add that add Y to the queue. So that's all. And then after the loop, I check whether I have added all n nodes. If I have, I will return answer. Otherwise, I will return an empty array as specified by in the problem description. So that's all.